لا تنسوا الإعجاب بالفيديو والاشتراك في القناة.
السلام عليكم ورحمة الله وبركاته. In this video we are going to discuss the oscillatory motion. Last year you have studied that there are two types of motion. Number one, translation motion, such as brain motion. Number two, periodic motion, such as the movement of the planets around the sun. The planet like Earth moves around the sun in regularly, or this motion is repeated regularly in equal periods of time. Every year it moves around the sun in equal period of time. So the periodic motion is the motion which is regularly repeated. Number one, it is regularly repeated. Number two, it is in equal periods of time. There are two types of periodic motion. Number one, oscillatory motion. Number two, wave motion. In this video we are going to discuss in particular the oscillatory motion. Activity number one, tools, a pencil. Activity number one, defining the concept of the oscillatory motion. Materials and tools. Number one, a pencil. Number two, 3 centimeter long thread. Number three, a quarter-pound coin. Steps: make a simple pendulum. The coin is fixed to the thread and the thread is fixed to the pencil. Number two, pull the coin to the right side of the rest of its rest position. Then leave it. Number three, use the stopwatch to record the time taken by the coin to repeat its movement several times. What you observe: the oscillating body moves around its original position, left and right, and this motion is repeated in equal intervals of time. The displacement of the oscillating body from A to B, and from B to A, and from A to C, and from C to A are equal. Number three, the velocity of the oscillating body A when it moves from A to B decreases. In other words, the velocity of the oscillating body when it passes through its original body A reaches its maximum, but when it reaches B, it is decreased regularly. The same thing to when it reaches C. The velocity in its rest position is maximum, but when it reaches C is reduced gradually. Conclusion: the oscillating body moves around its position where the motion is repeated through equal intervals of time. And we can find out that the oscillatory motion is the motion of the oscillating body around its rest position where the motion is repeated in equal intervals of time. We have three things: the motion is around its position, its rest position. Number two is repeated in equal intervals of time. We have some examples of the oscillatory motion. Number one, a spring. Two, time fork. Three, a pendulum clock. You can find other examples of the oscillatory motion on the internet. But the question here is: the motion of the rotary beam considered an oscillatory motion, and why? Activity 2. How can we represent the oscillatory motion graphically? Activity 2. Graphical representation of the oscillatory motion. Tools: a smooth paper, tape, rolled around two rules. Number 2, spring. 3, weight. 4, pencil. Steps: fix the pencil to the weight, then tie it at one end of the spring. The other end of the spring is fixed to the holder, so the pencil's tip touches the midpoint of the paper tape, as shown in this figure. Roll the paper regularly. Roll the paper regularly. Then pull the weight downwards. Pull the weight downwards and lift it. When we leave the weight, the spring go upwards and downwards. Go upwards and downwards. Through its motion, this graphic is drawn. This graphic represents the simple harmonic motion. When the spring goes up and down, it represents this graphic. This graphic is a graphic of the simple harmonic motion. So, the simple harmonic motion is considered the simplest form of the oscillatory motion. We have some concepts related to the oscillatory motion. Number 1, amplitude. 2, complete oscillation, periodic time. 4, frequency. We will discuss number 1, amplitude. In this picture, we find that the pendulum in position A is in its rest position. When it reaches B position and C position, C and B represent the maximum displacement reached by the oscillating body. So, when the oscillating body passes from A to B, from B to A, from A to C, and from C to A, we find that these displacements are equals. And each of one is called an amplitude. So, the amplitude is the maximum displacement done by the oscillating body, the maximum displacement made by the oscillating body away from its original point. In this figure, we can explain it more. The red line refers to the rest position of the oscillating body, and the blue line refers to the oscillating motion. When the body moves from A to B to A to C and so on, it passes through different points, but B represents the maximum displacement and C represents the maximum displacement. So from A to B is called amplitude. We can measure the amplitude using meter or centimeter. You can find out what is meant by the amplitude of an oscillating body is 2 centimeters. Number 2, complete oscillation. The pendulum, to make a complete oscillation, have to do 4 displacement. From A to B, from B to A, from A to C, and from C to A. But there is an important condition. The oscillating body has to pass by a fixed point on its path 2 successive times in the same direction. What does it mean? It goes from A to B, from B to A, from A to C, from C to A. This is called one complete oscillation. It passes through A 2 times in the same direction. You follow the arrows and you can understand it by yourself. So the complete oscillation equals 4 amplitude. You can find from the figure the complete oscillation equals 4 amplitudes. But if the oscillating body moves from A to B and from B to A, it equals half complete oscillation or half oscillation. And from B to C, from B to C equals half oscillation. Number 3, periodic time. If the oscillating body moves from its rest position to B in half a second. So it has to do for displacement to make a complete oscillation. Every displacement takes half a second. So we multiply half a second by 4 to have the time of the complete oscillation. This time to reach one complete oscillation is called periodic time. So periodic time is the time taken by an oscillating body to make one complete oscillation, and the unit used is a second. We can determine the periodic time by using another equation. Time in seconds divided by number of complete oscillations. So if we have all the time in seconds taken by the oscillating body to make a fixed number of complete oscillations, we can determine the periodic time. Number 4, frequency. Frequency can be determined by this equation: the number of complete oscillations divided by time in seconds. In other words, for example, if we have 50 complete oscillations made or done in 10 seconds, we can determine frequency by dividing 50 by 10 equals 5 complete oscillations per second. So 1 complete oscillation per second equals 1 hertz. Frequency is the number of complete oscillations made in 1 second, done in 1 second by the oscillating body. So the red line refers to the time, the blue line refers to the motion of the oscillating body. We can determine how the number of complete oscillations by counting the number of amplitudes. 1, 2, 3, 4. This is 1 complete oscillation. 1, 2, 3, 4. Number 2 of complete oscillation. So in this figure we have 2 complete oscillations. We can divide it by the time if it is known, so we can find out what frequency means. What is the relation between frequency and periodic time? We find that frequency, when it is multiplied by periodic times, it equals 1. We can represent it graphically by this graphic. So the frequency and periodic time are in an inverse relation. In other words, if the frequency decreases, the periodic time increases, and vice versa. You can concentrate on this figure, brain map to the periodic motion, and read it carefully. This is everything for today. Thank you.